Oh, he's not in here, Professor Feng Yu, which we're involved in this research. We're designing a novel system of energy storage which use RNG cold energy. Okay, let's see the overview of this research. When we are getting RNG from the other place, Korea is one of the most importer of RNG, which has minus 160 degrees of Celsius, so it has very low temperature. When we are going to use this RNG to the natural gas, it's about the atmospheric temperature, so a huge of the cold energy is wasted in conventional models. About 97% of existing model waste this cold energy because it's hard to use. It has a limited usage. So in this research, we suggested the air to liquefy using this cold energy to be cryogenic energy storage. So we're using surplus electricity to be consumed in compressor, and air get liquefied by the cold energy of LNG, so it can be stored in liquid air of the surplus electricity. And when we are going to use this stored energy, yeah, I think, sure, okay, yeah. We're gasifying this liquid air and expand by the expanders, so we're getting power by turbines. So we can use surplus electricity in nighttime, and we can use in the afternoon as this slide. As you all know, the energy demand significantly different over time. It's one of the example of U.S. energy demand curve. You can see the nighttime and the afternoon, it has almost twice difference because people are inactive in night and are active in the afternoon. So we're going to balance this energy difference by using energy storage system. And also there have been developed many kinds of energy systems from the supercapacitors to the pumped hydro power storage. It's based on the power capacity. So in case of scale of city or country, we're going to use the bulk power management system, which developed before. And in this research, we're focused on the cryogenic energy storage, which is the yellow one. And I introduced the design concept of this research. From the LNG storage to the natural gas in off-peak time where electricity demand is lower, the cold energy of LNG is transmitted to the liquefying air. So it has a surplus electricity to get air to be liquefied. It is compressed using electricity, and it's liquefied by using cold energy of LNG storage. So when it is stored in liquid air storage, and see the on-peak time, their on-peak time is relatively higher electricity demand, so we are not using electricity in here. Then we just stored cold energy to the intermediate storage to use this cold energy in the off-peak time. And also, in the liquid air storage, it generates electricity in on-peak time to the electrical grid by using the turbines to expand this stored liquid air. So it continuously produces natural gas as its original purpose, and also it can use as the energy bank. And the one important thing is here, intermediate storage, we need to define what kind of energy medium to be stored. So we select two bases as one is broad temperature range. So LNG has minus 160 degrees, so we need to have broad temperature range of using this cold energy. Also, we are going to use as high isobaric heat capacity to the volumetric efficient. As the common refrigerant and the carbonate, we choose the propane as the red one here because it had a wide temperature range and has relatively higher heat capacity. So this is for the storing cold energy from here to the intermediate storage. And it's a detailed design of the process. Let's see from each one in on-peak time operation. The LNG is pressurized and its cold energy is stored in intermediate storage, and it's going to be natural gas supplied to the industrial use or household use. So it's for the on-peak time. When in case of off-peak time, LNG goes the different way to the storing cold energy to the air. So the air, sorry, can I use? Yeah, sorry. Yeah. From the air, it consumes surplus electricity to the compressor, and it's pressurized to the 37 bar, and it liquefied from the cold energy of LNG, so it's stored in liquid air. And use cold energy, and the natural gas is going to be supplied. And when it is stored in here, we can use this module independently. As liquid air, we can release electricity by expanding it, because it has high pressure, and we're going to use a pump to pressurize more, and we're using turbines to produce electricity when the time of on-peak or the on-demand when you're using energy. Then the design basis we set as the reference before these journals. And we are going to calculate it based on the 1 million ton per year of the LNG regasification. Before calculating the result, we set optimization of the pressure ratios of each air compressor and turbines. There's 4 compressor and 4 turbines to optimize each of the pressure ratios. And the constraints are based on the equipment feasibility. So the power results shows like this one. We optimize the compression ratio and expansion ratio. In case of energy storage operation, we can store about 53 megawatt of power. When we use this stored energy, we can get 45 megawatt of power. It shows about 85% round-trip efficiency by using LNG cold energy. We're discussing it later. Let's see the thermodynamic first. These 2 figures shows the thermodynamic behavior of air in storage and release. When it goes, the atmospheric pressure of air goes in, and it is compressed through the compressor, liquefied by the LNG cold energy, and it becomes stored as liquid air. We can use it as energy release operation by pressurizing and gasifying it and expand it. It's a little bit similar like compressed air energy storage. So we can use the compressor to store energy, and we're using turbines to get energy back. And also, this figure shows the exchange flows of the air storage. There's about near zero of air with the compressing power. it becomes 37 bar of pressurized air. We get cold energy from the RNG and the intermediate storage. So we got cold energy, so liquid air becomes stored in here. We are using back this liquid air to get energy. Going this way, we got the turbine for, it's about 48 megawatt. So when we are seeing this performance, as seen, round-trip efficiency shows 85.1% of this proposed system, which is higher than existing cryogenic energy stores or the conventional bulk power management, which shows only 75% maximum. This improved round-trip efficiency is because of the using cold energy, which is wasted before in conventional process. So using this cold energy, we can get a higher round-trip efficiency. And this figure shows when it applied to the electrical industry in South Korea. As the South Korea's forecast demand is like this one, we can store about 2,000 megawatt of electricity, and we can release this amount when it applied to the proposed model. So in this figure, we can store this amount of energy in time of off-peak time. We can release it in the on-peak time by turbines. So this result shows the approximately 10% of non-base load power generation can be substituted. And we also did cost estimation of this process to see the economically feasible or not. We're based on the net present value model, and the sales contains the regasification fee and the electricity sales from the arbitrage. And the operating cost includes maintenance costs, including heating and electricity cost. And it is based on the reference and the Aspen capital cost analyzers with these models. And we also consider the plant cost index and also equipment life expectancy. And these are the cost factor we set as 25 years of operations. And this data is based on the South Korean data. And the bare mode factor and life expectancy of equipment as seen as this. And the result shows the positive MPV. It shows about 140,000 $. And its sales shows the regasification sales and an additional electricity sales from the arbitrage, because we are storing electricity in off-peak time and selling it in on-peak time. It has about twice different price change. And the IRR represents 17.7%, so I think it's quite economically feasible. Also, we did some sensitivity analysis for the cost estimation result. As you see the few factors in here, just excluding the regasification sales, there's the mostly electricity price and the capital costs mainly affect the cost of this proposed process. Normally, the electricity price of the on-peak time and off-peak time are very different, and it changes may affect the MPV results so much. So you can have more profit where these prices are different in regions. So the conclusion of this research, we developed a novel design of the energy regasification process integrate with the cryogenic energy storage by the air. So it is working like an energy bank, utilizing the energy cold energy. And the round-trip efficiency shows 85.1%, which is higher than existing bulk power management system. Because of using the energy cold energy, it can have improved round-trip efficiency. And applying this proposed system to case of South Korea, it can replace approximately 10% of non-base load power generation. So it can save fuels more than others. And also it's economically feasible, which shows 17.7% of internal return rate. And it is lucrative for the other regions, which shows significantly different electricity price. We can get more profit by arbitrage. And it also helps the enhancing electricity flexibility by storing surplus electricity in off-peak time. So we can use surplus electricity to get in on-peak time. Thank you for the listening. If you have questions, please ask me. Yes, please.
So could you go back to the last slide?
Yeah.
So I'd like to clarify the 2% reference you made there, 2% of non-base load power.
Yeah.
What does it exactly mean?
Ah.
What's the peak, for example?
Okay. Can you open the last slide? Yeah, actually, the non-base load power plants mean like natural gas power plant or cores. Like base load power plants mean the nuclear or the hydropowers, which operate all day, 24 hours. But non-base load power just operate in peak time.
So you show like roughly this
Yeah.
technology is still up to about 1,600 megawatts, right?
Yeah.
So what is that for peak demand in South Korea?
Peak demand. Well, it's working. Maybe go back to the here. Yeah. It's about 18,000 megawatt. 80,000 megawatt of whole South Korea electricity.
So this part can generate 1,600 buses, right? That's the ratio I understand. How much contribution this can make?
So this means there's the nuclear-based base load power generation, and also the burning fuels for non-base load power generation.
So you're assuming roughly
Yeah.
non-base load is roughly 16,000 megawatts.
This amount, yeah.
Okay, last question before we end the session, please. Eric Long, University of Virginia. Thanks very much for the talk. I wanted to ask a little bit about the efficiency, the 85%.
Yeah.
It seems like it's a pretty modest compression ratio that you're dealing with, so usually it has rather low efficiency, but by going to very low temperatures,
Yeah.
you're claiming to be a very high efficiency. I'm just worried about the energy transfer, if you're piggybacking off of LNG, you're taking energy from there. That's not really fair to account for that. So I'm wondering if there's been any experiments that could actually give some validation or credibility to such a high efficiency with a very low compression rate and compressor.
So your meaning of the equipment efficiency.
Sorry?
So your meaning of the compressor or turbines.
The cycle efficiency is 85%. Which is great. I just want to make sure I understand how to get that high.
Yeah. The compressor ratios of here.
Usually at those low compression ratios, the efficiency is very low. But you're claiming very high efficiency even though you have very low compression ratio.
With that as the constraint as here, the pressure ratio of compressor does not exceed 3 as the equipment feasibility.
I understand you're limiting
Yeah.
the compression ratio. How do you get such high? Maybe we'll have that discussion.
Or so you mean here?
So we will
Yeah, yeah.
continue this discussion about efficiencies in the break. We are a bit behind schedule, but that really doesn't matter because the break is too long anyway. So we'll see you.